Imagine you're gazing up at a clear night sky, seeing countless stars, entire galaxies, and then realizing that what you're actually seeing, all the bright, familiar stuff, makes up only about, well, 5% of the entire universe.
Just 5%. It's kind of staggering.
Yeah, that's right, 5%. The vast, overwhelming majority of everything out there, roughly 95%, is utterly invisible to us. That's our starting point today, a truly mind-bending fact. We're talking about a cosmic composition that includes just that 5% normal, visible matter, everything from you and me to planets, stars, and nebulae.
All the things we think of as the universe.
Exactly. Then there's about 27% dark matter and a whopping 68% dark energy. These aren't just minor footnotes, they're the dominant forces shaping the cosmos.
Absolute dominant.
Our mission for this deep dive is to untangle the powerful evidence for dark matter, explore some truly intriguing alternative ideas, and shed light on the cutting-edge scientific hunt to figure out what it truly is. The goal is really to give you a shortcut to being well-informed on one of the biggest, most fundamental puzzles in physics and astronomy. So, let's take a journey into the unseen.
It's a profound journey, indeed. And, the idea that something invisible is holding the cosmos together has actually been whispered about by scientists for a long time.
Right.
But the concrete evidence for it has grown exponentially in the last century. The very first hints of this cosmic mystery started surfacing back in the early 20th century. Astronomers like Jacobus Kapteyn in 1922 and Jan Oort in 1932 were already looking at how stars were moving within our own galaxy and realized there seemed to be more gravitational pull than the visible stars and gas could possibly account for.
So even back then, there was this quiet suspicion that something was off, a gravitational imbalance. But who really kicked off this dark matter conversation, gave it a name and a firm piece of evidence?
Well, that credit largely goes to the Swiss astrophysicist Fritz Zwicky in 1933.
Zwicky, okay.
Yeah. He was studying the Coma cluster, a massive collection of galaxies, and he applied something called the virial theorem.
The virial theorem.
Think of the virial theorem as basically a way to estimate the total mass of a system, like a galaxy cluster, by measuring the average speeds of its components, like the galaxies swirling around inside it.
Got it. So you measure how fast things are moving to figure out how much gravity and thus mass must be there.
Exactly. And what Zwicky found was astonishing. The galaxies in that cluster were moving so incredibly fast.
Faster than expected.
Way faster. So fast that if only the visible matter were present, they should have long since flown apart. The cluster shouldn't have been stable. It was like a carousel, where the horses on the outside were spinning at breakneck speeds and yet staying perfectly in place. He concluded there had to be an enormous amount of unseen mass, providing the extra gravitational glue to hold the cluster together. He famously coined the term dark matter, dunkel materie, in his original paper.
Dark matter, there it is.
Now, while his exact numbers were a bit off due to the technology of the day, his core insight that most of the mass was dark was absolutely correct.
Okay, that's a powerful start. So Zwicky gave us those first tantalizing hints. But what really brought this missing mass problem to the forefront decades later was the meticulous work of astronomers like Vera Rubin, especially with galactic rotation curves.
Yes, Rubin's work.
What did her observations mapping how galaxies spin reveal that was so, well, profoundly perplexing?
Rubin's work was absolutely pivotal. She painstakingly mapped the rotation speeds of spiral galaxies using neutral hydrogen emissions, which let her see further out than just the bright stars. Now, if the visible stars and gas were all there was, you'd expect the rotation speed to decrease as you move further out from the galactic center.
Like planets around the sun, Mercury zips around, Neptune crawls.
Exactly like that. Slower the further out they are. But what she consistently observed, galaxy after galaxy, was that the velocities remained constant, flat, even at the very edges of galaxies, where there was little to no visible matter.
So the outer stars were moving just as fast as the inner ones. That doesn't make sense with just the visible stuff.
It makes no sense at all. It wasn't just a small discrepancy. It was a fundamental contradiction to what Newtonian physics predicted based only on the luminous stars and gas.
This isn't just a minor component, then. It's literally the dominant gravitational force shaping the entire galaxy's dynamics. That's a profound shift in perspective, isn't it?
Precisely. This strongly suggested that each galaxy isn't just the visible disk you see, but is actually embedded within a vast, unseen halo of dark matter. Yeah, these halos are thought to be diffuse and sort of spheroidal, densest at the centers and gradually thinning out, extending far beyond the visible galaxy itself. The stars and gas we observe are just sitting within this much larger gravitationally dominant structure.
Okay.
And if we connect this to the bigger picture, it's not just about individual galaxies. What's truly fascinating here is that without dark matter, the early smooth universe wouldn't have had enough gravitational pull for ordinary matter to clump together in the first place.
Really? So no galaxies without it?
It simply couldn't form the galaxies, stars, and planets we see today, or at least not nearly as quickly or efficiently. Think of dark matter as a kind of cosmic architect,
I like it.
forming a gravitational scaffold or a vast web-like structure that winds through the universe, attracting normal matter. These dark matter halos are essentially the seeds of galaxy formation, making modern cosmic structures possible.
That's a beautiful way to put it, a gravitational scaffold. So we have all these indirect clues, these gravitational fingerprints, but is there anything that feels more like direct evidence? Something that really shows dark matter behaving differently from the stuff we can see?
There absolutely is, and that brings us to the bullet cluster.
Ah, yes, the bullet cluster. I've heard this is a key piece of evidence.
It really is. This is truly a cosmic forensic scene, a galactic smash-up that gives us a direct look at dark matter in action. It's the result of two galaxy clusters colliding at incredible speeds.
A cosmic car crash in slow motion?
Kind of, yeah.
Yeah.
And what's remarkable is that in this collision, the individual stars, because they're tiny points with vast spaces between them, they largely pass right through each other.
Okay, stars miss each other mostly.
Right. But the hot gas, which is ordinary baryonic matter, makes up most of the visible mass in these clusters. It slams into itself. It interacts electromagnetically.
Like friction, almost.
Sort of, yeah. It slows down due to this interaction, forming a distinct, hot bullet shape, which glows brightly in X-rays. You can see it in the images, often colored pink.
Okay, so the stars go through, the gas collides and slows down, forms this glowing bullet shape. But what does the gravity tell us? Because that's where dark matter should show up, right?
Exactly. That's the crucial part.
Yeah.
When scientists used gravitational lensing, which we should definitely talk more about, to map the total mass distribution,
Where the gravity actually is.
precisely, they found that gravitational mass wasn't centered on the glowing hot gas. It was concentrated in separate regions, significantly offset from that gas.
Whoa.
This is the smoking gun. It implies that the dark matter, being collisionless or nearly so.
Meaning it doesn't interact electromagnetically like the gas.
Correct. It passed straight through the collision, relatively unaffected, bypassing the slowed-down gas. It behaved differently from ordinary matter, only interacting gravitationally.
So the gravity map shows the dark matter sailed right through, while the normal matter got stuck in the middle.
That's the picture. It's incredibly strong empirical support for dark matter existing and being fundamentally different from baryonic matter.
It's almost mind-boggling how many independent lines of evidence all point to the same invisible answer, isn't it? It's like the universe is shouting dark matter from every corner.
It does feel that way sometimes.
Mhm.
And speaking of gravitational lensing, it's such a key tool here, as I just
Yeah.
mentioned.
Right, you said they used it for the bullet cluster map. How does that work exactly?
Well, for you, our listener, gravitational lensing is simply a phenomenon predicted by Einstein's theory of general relativity. Massive objects like galaxy clusters or even individual galaxies warp space-time around them.
Bending space itself.
Yep. And that warped space-time, in turn, bends the path of light from more distant objects behind them. This distortion can make background objects appear stretched, create multiple images of the same galaxy, or even form giant arcs.
Like those amazing pictures from Hubble.
Exactly, like those seen in Galaxy Cluster Able 370. This is what we call strong lensing.
Okay, strong lensing gives those dramatic effects. What about the weak version you mentioned?
Then there's weak lensing, where the distortions are much more subtle, almost imperceptible if you just looked at one background galaxy. But by analyzing these tiny correlated distortions across many background galaxies,
Statistically.
right, statistically, we can create detailed maps of how mass is distributed on much larger scales. And this raises an important point. Gravitational lensing allows us to map the distribution of mass independent of whether that mass emits light.
So it sees everything that has gravity, bright or dark.
Precisely. It's a truly unique and powerful probe for seeing the invisible. Hubble, and now JWST, have been instrumental in creating detailed dark matter maps using lensing. These maps reveal that dark matter forms smaller clumps or substructures than previously known, which actually supports predictions of the cold dark matter theory.
Okay, so lensing gives us this incredible map of dark matter across cosmic time. But if we want to look even further back to the universe's absolute infancy, to a time before stars even existed, There's another crucial piece of evidence, isn't there? The cosmic microwave background.
Absolutely. The cosmic microwave background, or CMB.
The CMB, tell us about that.
The CMB is often called the afterglow of the Big Bang. It's essentially a cosmic baby picture, a snapshot of the universe when it was just about 380,000 years old.
Wow, ancient light.
Very ancient. It's from the moment when the incredibly hot, dense, early universe cooled enough for neutral atoms to form. Before that, it was an opaque plasma. Light couldn't travel freely. But once atoms formed, light decoupled and traveled, and that light, stretched by cosmic expansion, is what we see today as the CMB microwaves.
And this baby picture tells us about dark matter.
Oh, yes. The CMB is perhaps the most compelling evidence for dark matter, allowing us to probe its role in the universe's infancy with incredible precision. You see, the CMB isn't perfectly uniform. It has tiny temperature anisotropies.
Little hot and cold spots.
Exactly. Tiny fluctuations in temperature, first detected properly by the Kobe satellite in 1992, and then measured with exquisite detail by WMAP and Planck satellites. These fluctuations reveal a pattern of acoustic peaks.
Acoustic peaks, sound waves in the early universe.
Sort of, yeah. Pressure waves rippling through that primordial plasma. The locations and heights of these peaks in the CMB power spectrum depend critically on the universe's fundamental parameters, its composition, its geometry.
Including how much dark matter there is.
Precisely. The fact that these observations align so perfectly with the lambda CDM model, our standard cosmological model, is a huge validation for it. This model tells us the universe is made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. And crucially, the CMB data also indicates that the geometry of the universe is approximately flat.
Flat, meaning like a sheet of paper, not curved like a ball or a saddle.
On the largest scales, yes. If you could draw a truly colossal triangle across the cosmos, its angles would add up to 180 degrees. And achieving that flatness, given the matter we see, requires the specific amounts of dark matter and dark energy predicted by lambda CDM. That cosmic baby picture essentially tells us that 5/6 of the total matter in the early universe had to be this non-interacting dark form.
Okay, so just to recap that standard picture.
Yeah.
The lambda CDM model, our universe's standard cosmological blueprint, describes a cosmos dominated by dark energy, that's the lambda, and cold dark matter, that's the CDM. And when we say cold, we mean these dark matter particles are slow-moving, right? Moving much slower than the speed of light.
That's right, which allows them to clump together effectively under gravity and form the vast structures we see, like those gravitational scaffolds we talked about. Hot, dark matter, moving faster, would tend to smooth things out too much.
But okay, lambda CDM is the standard model, hugely successful. But what about those who question the very existence of dark matter? What if gravity itself just behaves differently on large scales?
That's where modified Newtonian dynamics, or MOND, comes in. It's an alternative gravity theory, first proposed by Mordechai Milgram back in the 80s.
Oh, MOND.
MOND proposes to explain phenomena like those galaxy rotation curves we discussed, not by adding invisible matter, but by modifying gravity itself, specifically Newton's law of gravity, or maybe inertia, at very, very low accelerations.
So the acceleration you feel at the edge of a galaxy is so tiny that maybe gravity just works differently there.
That's the core idea.
Yeah.
And it's compelling because it works surprisingly well for explaining the rotation curves of individual galaxies without needing any dark matter halos.
So instead of a missing ingredient, MOND suggests we need a new recipe for gravity under certain conditions. But if it's just a modified gravity, how does it stand up to all the other evidence we've talked about? Like the bullet cluster, or the CMB.
Right, and that's where MOND faced significant challenges for a long time. While it explained galaxy rotation, it struggled to account naturally for gravitational lensing in galaxy clusters, where mass maps clearly show something beyond the visible matter, and critically, it couldn't reproduce the precise details of the cosmic microwave background data. Those acoustic peaks were a major hurdle.
So MOD was good locally, but struggled cosmologically.
For a while, yes. However, science evolves. Very recently, researchers Tom Zuznik and Konstantinos Skordis constructed a relativistic MOND theory, one compatible with Einstein's relativity that can actually reproduce the CMB data.
Oh, really? So MOD is back in the game for the CMB.
Well, it's more complex. What's fascinating about their approach is that to make it work, their theory includes an invisible ingredient, something extra beyond just modifying gravity. This ingredient acts effectively like dark matter on cosmic scales, helping to form structure and match the CMB.
Huh. So it's like MOND plus something that mimics dark matter.
In a way, yes. It effectively blurs the line between the dark matter and MOND paradigms. It was a really interesting development, showing how these alternative ideas are pushing the boundaries.
So MOND offers one fascinating way to rethink gravity, perhaps avoiding dark matter altogether in some contexts, or maybe merging with it in others. But what if the challenge isn't just about tweaking gravity, but about something even more fundamental? What happens when galaxies themselves seem to break the rules of dark matter by simply not having any?
Indeed, that's another genuine puzzle. We found a few galaxies, like DF2 and NGC DO52 DF4, often called DF4.
Galaxies without dark matter.
They appear to lack significant dark matter based on the motions of their stars or star clusters. Their mass seems to be almost entirely accounted for by their stars.
But wait, didn't we just say galaxies need dark matter halos to form?
Exactly. This completely challenges conventional galaxy formation theories, which suggest all galaxies should form within these vast dark matter halos. How do you form a galaxy without its gravitational scaffold? It's a real mystery.
Are there explanations?
Well, there are theories. Some scientists suggest that the dark matter in these particular galaxies might have been stripped out by strong tidal forces from a larger nearby galaxy during a past interaction, like the big neighbor stole its dark matter halo.
Okay, so maybe they had dark matter but lost it.
That's one possibility. But these objects definitely remind us that while the overall evidence for dark matter is robust, the universe always has new surprises and complexities. We don't have all the answers yet.
These exceptions truly keep scientists on their toes. So, okay, the evidence for dark matter's existence feels incredibly strong, despite these puzzles. But its identity is still this huge, open question. We've mentioned it's cold, non-interacting mostly. But what are the leading candidates for what this invisible stuff actually is, particle-wise?
The microscopic identity of dark matter.
Yeah.
Yeah, that remains one of science's greatest unsolved mysteries. We're definitely talking about physics beyond the standard model of particles.
Beyond our current understanding of fundamental particles.
Absolutely. For decades, the leading candidate has been WIMPs, or weakly interacting massive particles.
WIMPs. Heard that term a lot.
Yeah. These are hypothetical particles predicted to be, well, massive, maybe tens to hundreds of times the mass of a proton, and interact very, very weakly with ordinary matter, primarily through gravity and the weak nuclear force, hence the name.
Okay, heavy and elusive. What else?
Another prominent candidate gaining a lot of traction is axions. These are hypothetical ultralight particles, vastly less massive than WIMPs, potentially billions or trillions of times lighter than an electron.
Ultralight. That sounds very different.
Very different. They're theorized to interact potentially via the electromagnetic force, very weakly, and gravity. They arise naturally in theories trying to solve other problems in particle physics, like the strong CP problem.
And didn't you mention black holes?
Right. Primordial black holes are another possibility. These aren't the black holes formed from collapsing stars today, but hypothetical black holes that might have formed from density fluctuations in the very early universe moments after the Big Bang.
Could they be the dark matter?
They could contribute, certainly, especially after the detection of merging black holes by gravitational wave observatories like LIGO and Virgo spurred new interest. However, whether they can constitute all of the dark matter is still heavily debated and constrained by various observations, like microlensing surveys.
So it's like a cosmic whodunit with multiple suspects, WIMPs, axions, primordial black holes.
Pretty much. And there are other ideas, too, like sterile neutrinos or even more exotic possibilities.
And this is where the wave-particle duality, a fundamental concept in quantum physics, gets even more intriguing, right? For particles with incredibly low mass, like axions, their wave-like behavior could manifest on truly cosmic scales.
Exactly. Everything has both particle and wave properties, but the wavelength, the de Broglie wavelength, is inversely proportional to momentum. For very massive particles like WIMPs, the wavelength is tiny. But for ultralight particles like axions, their wavelength could be huge, even galaxy-sized. This could lead to different behavior in how structures form or how gravitational lensing works.
So could gravitational lensing, for example, help us tell the difference between these suspects? Could it distinguish between clumpy WIMP dark matter and wavy axion dark matter?
Potentially, yes. The distribution of WIMPs versus, say, ultralight axions might subtly differ and affect lensing patterns, particularly on small scales. WIMPs might form lots of small clumps, while wave-like dark matter might smooth things out a bit below its characteristic wavelength.
And has lensing actually shown anything like that?
Well, there was a fascinating study in 2023 led by Alfred Amruth and colleagues. They examined the quasar HS 0810S plus 2E554, which is being gravitationally lensed by a foreground galaxy, creating multiple images. They analyzed the precise positions and brightnesses of these images.
Hmm.
They found that the specific lensing patterns observed were better explained by axions, specifically wave-like dark matter, than by the standard cold dark matter model typically associated with WIMPs.
Wow, so an early clue potentially pointing towards an axion or something like it.
Potentially. It's very suggestive, very exciting work. But, and this is a big bet, one system is far from conclusive. Science demands extraordinary evidence for such a profound claim. We need many more observations analyzing different lensing systems to truly see if this holds up.
Sure, reproducibility is key.
Absolutely. And on a related note, we can also use these cosmic collisions, like the bullet cluster or others, to try and measure dark matter's self-interaction, meaning, does dark matter bump into other dark matter particles, not just normal matter?
Does it interact with itself?
Right. Richard Massey and his team have done important work on this. If dark matter were to interact with itself significantly, like the hot gas does, it would also slow down during a cluster collision.
But we said it seemed to sail through in the bullet cluster.
Exactly. Observations, including recent refinements from the James Webb Space Telescope of the bullet cluster, strongly indicate no significant self-interaction for dark matter. It seems to just pass right through itself, behaving almost like ghosts in that respect. Massey's team even used a telescope called SuperBit, flown on a high-altitude balloon, specifically to map dark matter using weak lensing in cluster collisions.
Superbit, wasn't that the one with the dramatic landing?
That's the one. It had a rather bumpy landing in Argentina after its final flight, but thankfully the crucial data was recovered, and it helped confirm those minimal self-interactions. Science in action.
That's a great anecdote and a fantastic example of the ingenuity and sometimes sheer luck involved in this field. So, okay, we've got the theoretical suspects, WIMPs, axions, maybe others, and we're looking at their cosmic behavior through things like lensing and collisions. But if dark matter is truly out there and interacting, however weakly, could we actually catch it in a lab here on Earth?
That's the billion-dollar question, isn't it? And that's the goal of direct detection experiments.
Direct detection. Trying to grab one.
Essentially, yes. The principle is elegant in its simplicity, but incredibly challenging in practice. We're trying to search for the faint, low-energy recoils of atomic nuclei that would be caused by a WIMP, or perhaps another dark matter particle colliding with an atom in a detector.
Like a cosmic billiard ball hitting a nucleus.
A very, very tiny nudge from a very, very elusive billiard ball. Imagine an atom in a huge, ultra-pure tank of liquid xenon, or maybe a crystal cooled to near absolute zero, getting this tiny, almost imperceptible kick from a passing dark matter particle. This kick might create a tiny flash of light, scintillation, or a tiny vibration, heat, or phonons, that sensitive detectors can then pick up.
Sounds incredibly difficult.
It is. These signals are expected to be extremely rare and very low energy. That's why experiments like the Xenon series, LUX, PanX, and the upcoming LZ and Darwin experiments use vast tanks of super-purified liquid xenon or argon, buried deep underground in mines or tunnels.
Why deep underground?
To shield the detectors from cosmic rays and natural background radiation coming from the surface and the surrounding rock. Those background signals would completely swamp the faint signature of a potential dark matter interaction. It requires building these almost perfectly clean, quiet underground cathedrals to listen for the faintest whispers from the dark sector.
And what about for axions? They're much lighter. Do these experiments look for them too?
Not typically with the same method. Because axions are so light, they wouldn't cause a nucleus to recoil noticeably. For axions, experiments like ADMX, Axion Dark Matter Experiment, use a different approach. They employ extremely strong magnetic fields within resonant cavities. The idea is that if an axion passes through this strong magnetic field, it might convert into a detectable microwave photon, a tiny flash of light at a specific frequency.
Like tuning a radio to find the axion station.
That's a great analogy. They slowly scan different frequencies, listening for that faint signal. It's another monumental effort requiring incredible technological precision.
Okay, so that's direct detection, trying to physically catch a dark matter particle hitting a detector. What if we can't catch it, but we can see the smoke at least behind out in the cosmos?
Exactly. That's the complementary strategy called indirect detection experiments.
Looking for the byproducts.
Precisely. Instead of catching the particle itself, we're looking for the observable products of dark matter self-annihilation or decay happening out in space. If dark matter particles collide and destroy each other, annihilate, or perhaps if they are unstable and simply decay over vast time scales.
They might produce particles we can see.
Right. They might produce particles like high-energy gamma rays, or particles of antimatter like antiprotons or positrons, or even high-energy neutrinos.
And where would we look for these signals?
We look in places where dark matter is expected to be highly concentrated. Dense regions like the center of our Milky Way galaxy, or dwarf spheroidal galaxies which are thought to be dominated by dark matter, or even potentially annihilations happening in the Sun or the Earth's core if dark matter gets captured there.
So telescopes looking for gamma rays or antimatter.
Exactly. Space telescopes like the Fermi Gamma Ray Space Telescope, Fermi-LAT, and ground-based gamma ray telescopes scan the skies for unusual excesses of gamma rays that can't be explained by known astrophysical sources. Antimatter detectors like PAMLA, or the AMS experiment on the space station, look for excesses of positrons or antiprotons.
And neutrinos. You mentioned neutrino telescopes.
Yes, huge neutrino telescopes like IceCube at the South Pole or Super Kamiokande in Japan search for high-energy neutrinos coming from these dense regions. Neutrinos are particularly interesting because they travel directly from their source without being deflected by magnetic fields or easily absorbed, so they carry a pristine message.
Have any of these indirect searches found definitive evidence?
There have been some intriguing hints and excesses reported over the years, like a possible gamma ray signal from the galactic center or the positron excess seen by Pamela and AMS. However, attributing these definitively to dark matter is tricky, as ordinary astrophysical processes, like pulsars, could potentially explain them too. So far, no conclusive smoking gun signal has been confirmed via indirect detection, but the searches continue to get more sensitive and set important limits. Super Kamiokande, for instance, has set very strong limits on dark matter self-annihilation cross-sections, especially for lower mass WIMPs.
Okay, so direct detection tries to catch it here. Indirect detection looks for its effects out there. What about smashing particles together to create dark matter itself? This is where collider searches, like those at the Large Hadron Collider or LHC, come in, right? Can we actually make dark matter here on Earth?
That's the hope with collider experiments like ATLAS and CMS at the LHC and CERN.
How does that work? If dark matter is invisible and weakly interacting, how do you know if you've made it?
Good question. Here we're not directly observing the dark matter particles themselves because, as you said, they'd likely just fly out of the detector without leaving a trace. Instead, we search for them indirectly by looking for what we call missing energy and momentum.
Missing energy. How can energy be missing?
Well, in these incredibly energetic proton collisions of the LHC, we know the total energy and momentum going in. We then meticulously measure the energy and momentum of all the visible particles flying out into the detector components. If dark matter particles, and maybe neutrinos, are produced and escape undetected, they carry away energy and momentum. This leads to an apparent imbalance. The energy and momentum we measure coming out doesn't match what went in.
So you look for collisions where something invisible seems to have escaped, carrying away energy.
Exactly. It's like seeing debris fly out from an explosion, but noticing it's all recoiling in one direction, implying something unseen shot out the other way. We look for events with, for example, a jet of particles or a Z boson recoiling against nothing visible. That nothing could be dark matter.
Is this connected to theories like supersymmetry?
Very much so, historically. Many theoretical frameworks beyond the standard model, like supersymmetry or CUANA, naturally predict the existence of new, stable, weakly interacting particles that would behave just like WIMP dark matter. Often, the lightest supersymmetric particle, LSP, in these models is a perfect WIMP candidate. So many LHC searches are specifically looking for signatures predicted by CVY or similar theories that include dark matter candidates.
And have they found anything yet at the LHC?
Despite extensive searches during LHC's Run 1 and Run 2, analyzing vast amounts of data, no conclusive excess of events beyond the standard model predictions has been found yet. The parameter space for many simple WIMP models, especially those motivated by CUI, has been significantly constrained.
So no discovery yet, but they're pushing the boundaries.
Precisely. Future LHC runs, including the ongoing Run 3 and the upcoming high-luminosity LHC upgrade, will collect vastly more data and probe collisions at even higher energies. This will significantly increase the sensitivity, allowing us to search for even rarer dark matter production processes or explore different theoretical scenarios. The hunt continues on all fronts, direct, indirect, and collider. The ingenuity in designing these incredibly complex experiments just to catch a glimpse of something that barely interacts with anything is truly astounding.
What an incredible journey we've taken. I mean, from those first whispers of unseen mass in the cosmos, thinking about Zwicky and Rubin,
Hmm.
to the meticulous mapping of its gravitational influence with the most advanced telescopes like Hubble and Webb, looking at lensing and the CMB.
Yeah, big picture evidence.
And now to the deep underground labs and giant colliders hunting for its fundamental particles. This deep dive has truly, I hope, offered you, our listener, a shortcut to understanding one of the most fundamental questions about our universe. It really shapes how we perceive reality and the very fabric of existence.
It absolutely does. We've mapped the universe's structure. We think we understand its evolution pretty well based on lambda-CDM, and yet the majority of it, the dominant components of mass and energy, remain a profound mystery.
Yeah.
This quest for dark matter isn't just about finding a new particle to add to the zoo. It's about potentially uncovering entirely new physics beyond the standard model. It could fundamentally alter our understanding of what the universe is made of, and perhaps even how gravity works, or reveal new forces of nature. It forces us to reconsider the very building blocks of reality. It's humbling, really.
It truly is. It leaves us with such an exciting question, doesn't it? What surprising aha moment awaits us in this cosmic hunt? Will it be a WIMP signal underground, an axion detection, something from the LHC, or maybe something completely unexpected from astronomical observations? And how will that discovery, whatever it is, reshape our entire cosmic story?
That's the thrill of the search. We just don't know what's around the corner.
Thank you for diving deep with us today into this incredible mystery.